Hello. I will continue our exploration of the emergence of quantum mechanics. In the last class, we discussed the blackbody radiation problem and how the classical Rayleigh-Jeans model failed to predict the observed spectrum, resulting in the so-called ultraviolet catastrophe. To resolve this paradox, Planck introduced his pioneering model by proposing discrete energy states, or energy quantization, expressed as E equals nh nu, where n is an integer. Thanks to this quantum hypothesis, the ultraviolet catastrophe was resolved, and Planck's model successfully matched experimental data. Moreover, Planck's formula is consistent with the Rayleigh-Jeans model in the limit of large wavelengths and also aligns with the Stefan-Boltzmann law, tying it well into established thermal radiation theory. In this lecture, we will briefly discuss other important examples related to the emergence of quantum mechanics. The second major phenomenon is the photoelectric effect. When light shines on a metal surface, electrons are ejected, creating a photocurrent. Classical wave theory predicted that a higher light intensity, meaning a stronger electromagnetic wave, should impart more kinetic energy to the electrons, thereby increasing the stopping voltage V0. However, experiments revealed completely different results. First, increasing light intensity increases the saturated current, but has absolutely no effect on the stopping voltage. Second, the stopping voltage varies linearly with the frequency of the light, not its intensity. Third, there exists a strict threshold frequency. If the light's frequency is below this threshold, 0 electrons are emitted, no matter how intense the light is. To explain this, Albert Einstein proposed that light is not just a continuous wave, but is composed of localized, discrete packets of energy called photons. In this experimental result, the stopping voltage can be simply explained as the photon energy h nu minus the work function W. Next, let's discuss the Compton effect. Consider a single electron initially at rest, with an incoming photon approaching it. When the photon collides with the electron, energy and momentum are exchanged between them. The photon scatters at an angle theta relative to its original direction, while the electron recoils accordingly. To describe this interaction, we apply the conservation laws of energy and momentum. But how do we express the momentum of light? According to Einstein's special relativity, the total energy E of a particle relates to its momentum p and rest mass m as follows. E equals the square root of mc squared plus pc squared. For a photon, which has 0 rest mass, or m equals 0, this reduces to E equals pc, meaning the photon's momentum can be written as p equals E over c, which equals h over lambda. Thus, the energies and momenta of both the electron and the photon can be described precisely in this manner. From the perspective of classical electromagnetism, when an electromagnetic wave strikes an electron, the electron oscillates at the wave's frequency, with no change in the wavelength of the scattered wave. So lambda I equals lambda f. However, Compton's experiments revealed that the scattered photon has a longer wavelength than the incident photon. Lambda f is greater than lambda I, demonstrating that photons carry momentum and that their collisions with electrons change both the photon's wavelength and the electron's momentum. Let us now quantitatively analyze the principles of energy and momentum conservation in Compton scattering, following the step-by-step calculation shown on the slide. The vector p sub I of the initial photon momentum is equal to the sum of the final momenta of the recoiled electron, vector p prime, and the scattered photon, vector p sub f. Vector p sub I equals vector p prime plus vector p sub f. Moving p sub f to the other side and taking the square of both sides, we get p prime squared equals p sub I squared plus p sub f squared minus 2 p sub I p sub f cosine theta. Expressing the momenta in terms of wavelength, remembering that photon momentum is p equals h over lambda, we write p prime squared equals h over lambda sub I squared plus h over lambda sub f squared minus 2 times h over lambda sub I times h over lambda sub f cosine theta. Grouping and simplifying leads to p prime squared equals h over lambda sub I minus h over lambda sub f squared plus 2 times h over lambda sub I times h over lambda sub f, 1 minus cosine theta. Next, using the energy conservation principle, the total energy before collision equals that after collision. The initial electron energy E plus the incident photon energy EI equal the scattered electron energy E prime plus the scattered photon energy EF. According to the energy and momenta of the electron and photon, we can write the energy conservation in this manner, where mc squared is electron rest energy, h nu I is incident photon energy, h nu f is scattered photon energy, and square root of mc squared squared plus p prime c squared is the recoiled electron's total energy. Moving h nu f to the other side and then squaring the equation gives mc squared squared plus p prime c squared is equal to mc squared plus h times nu I minus nu f all squared. Expanding the right side, mc squared squared plus 2h times nu I minus nu f times mc squared plus h squared times nu I minus nu f all squared. The common term mc squared squared cancels out. Rearranging, the electron's momentum squared becomes p prime squared is equal to 2mh times nu I minus nu f plus h over c squared times nu I minus nu f all squared. Using the relation between frequency and wavelength, nu equals c over lambda, we rewrite the electron momentum squared as p prime squared equals 2mh over c times 1 over lambda I minus 1 over lambda f plus h squared times 1 over lambda I minus 1 over lambda f squared. Comparing this expression with the momentum conservation formula, the common term cancels out. Finally, this yields the famous Compton wavelength shift formula. Lambda f minus lambda I equals h over mc times 1 minus cosine theta, where h over mc is the Compton wavelength of the electron, about 2.4 picometers. This step-by-step derivation quantitatively demonstrates how energy and momentum conservation govern Compton scattering, confirming the particle nature of light. Now let's shift our focus from light to the structure of matter, the Bohr model of the hydrogen atom. Ernest Rutherford proposed a classical planetary model where electrons orbit the positive nucleus, just like planets orbit the sun. However, classical electrodynamics states that any accelerated charged particle, and an electron in circular motion is constantly accelerating, must continuously emit electromagnetic radiation. Based on the Larmore's formula shown here, we can estimate the stability of atoms. We start with the Larmore's formula for the power radiated by an accelerating charge. P equals minus q squared a squared over 6 pi epsilon 0 c cubed, where q is the charge, a is the acceleration, and epsilon 0 is the vacuum permittivity. Starting with the equation mr omega squared equals e squared over 4 pi epsilon 0 r squared, this expresses the balance between the centripetal force acting on an electron moving in a circular orbit and the Coulomb attractive force between the electron and the nucleus. From this force balance, the acceleration a of the electron can be written as a equals r omega squared, which equals e squared over 4 pi epsilon 0 mr squared, which shows that the centripetal acceleration equals the Coulomb force per unit mass. The power P radiated by this accelerating charge is given by Larmore's formula. P equals dE over dt, which equals minus e squared a squared over 6 pi epsilon 0 c cubed. By substituting the expression for A into this formula, we relate the radiated power directly to the system parameters. Meanwhile, the energy, E, of the electron is composed of its kinetic energy minus the electrostatic potential energy, given by E equals 1/2 mv squared, minus E squared over 4 pi epsilon naught r. Substituting V equals R omega leads to E equals 1/2 mr squared W squared minus E squared over 4 pi epsilon naught r. Using the balance of forces in circular motion, the centripetal force equals Coulomb's force. The energy simplifies to E equals negative E squared over 8 pi epsilon naught r. We then consider the rate of change of energy, dE dt, which is related to the power radiated, P. dE dt equals E squared over 8 pi epsilon naught r squared times dr dt, and m over 2 times E squared over 4m pi epsilon naught r squared times dr dt. This expression relates the rate of change of the electron's energy, dE dt, to the change in its orbital radius, dr dt. Comparing with our expression from Larmor's formula, and we can get the expression of the radial velocity, dr dt. Negative E squared over 3 pi m squared epsilon naught c cubed times E squared over 4 pi epsilon naught r squared. This negative sign indicates that the radius decreases over time. The electron spirals inward as energy is radiated away due to acceleration. By rearranging the variable r to the left side of the equation, we set up an integral of the radius ranging from the hydrogen atom radius A0 down to 0. Defining the total time taken for this process as t, we can express the calculation of t as an integral over dr and dt. Substituting the hydrogen atom radius A0, approximately 0.43 times 10 to the minus 10 meters, and calculating the integral leads to an estimate of the collapse time t of roughly 10 to the minus 11 seconds. This calculation shows that classical electromagnetism predicts atoms to collapse almost instantaneously, which contradicts observed atomic stability. This paradox emphasizes the need for quantum theory to explain atomic structure and stability. To resolve this, Niels Bohr introduced 3 bold postulates in 1913. Postulate 1. Electrons can only orbit the nucleus in specific, non-radiating, stationary orbits. While in these orbits, they do not emit any radiation. Postulate 2. The orbital angular momentum, L, of the electron is strictly quantized in integer multiples of h bar, meaning L equals mvr equals nh bar. Postulate 3. An electron can only change its energy state by jumping from one stationary orbit to another. When it jumps, it emits or absorbs a single photon carrying the precise energy difference, delta E equals h nu equals h bar omega.
Let us now calculate the atomic radius and energy levels according to the Bohr model. The equation here shows the electrostatic force between the electron and the proton in a circular orbit given by 1 over 4 pi epsilon 0 E squared over r squared equals mv squared over r. Applying the second postulate, quantized angular momentum, the numerator can be related to the quantized term, which, given the angular momentum squared, that is, mvr squared, becomes n squared h bar squared over mr cubed. Next, this relation is rearranged to express the radius, r, of the electron's orbit as r equals 4 pi epsilon 0 h bar squared over me squared times n squared, where n is the principal quantum number. This formula approximates to about 0.53 angstrom for the ground state, n equals 1, known as the Bohr radius. Next, the energy E of an electron orbiting the nucleus, as derived, is given by E equals negative E squared over 8 pi epsilon 0 r.
If we substitute the expression for r previously obtained into this formula, we get E equals negative of E squared over 8 pi epsilon 0 times me squared over 4 pi epsilon 0 h bar squared times 1 over n squared, showing that energy is quantized and inversely proportional to the square of the principal quantum number. Introducing the dimensionless fine structure constant alpha equals 1 over 4 pi epsilon 0 times E squared over h bar c, which is approximately equal to 1 over 137. The energy can also be expressed as E equals negative 1/2 times alpha squared mc squared times 1 over n squared, which is approximately equal to negative 13.6 over n squared, eV, which matches the well-known values for hydrogen atomic energy levels.
The change in energy, delta E, between two levels, Ni and Nf, is delta E equals E sub Ni minus E sub Nf, which equals Hc over lambda, or 1/2 alpha squared mc squared times 1 over Nf squared minus 1 over Ni squared. Rearranging to solve for the wavelength, lambda, we obtain the Rydberg formula. 1 over lambda equals Ry times 1 over Nf squared minus 1 over Ni squared, where Ry is the Rydberg constant, effectively explaining the hydrogen emission spectra. The Bohr model has several important limitations. First, it can accurately explain only hydrogen and hydrogen-like atoms, but it fails for multi-electron atoms. Second, it cannot account for the fine structure of spectral lines or their varying intensities. Third, it cannot explain the Zeeman effect and Stark effect, where spectral lines split in magnetic or electric fields. Finally, the model assumes that electrons move in fixed circular orbits, which contradicts the principles of quantum mechanics and the Heisenberg uncertainty principle. Therefore, the Bohr model was eventually replaced by the modern quantum mechanical model of the atom.
To wrap up today's lecture, let's summarize the 4 foundational milestones that led to the emergence of quantum mechanics. Blackbody radiation forced us to introduce quantized energy states for radiation oscillators. The photoelectric effect successfully introduced the concept of the photon as a localized packet of light energy. The Compton effect confirmed the particle-like momentum of photons, establishing wave-particle duality. The Bohr model successfully applied quantization to atomic structures, explaining the stable orbits of electrons. Together, these phenomena broke the foundations of classical physics and opened the door to the quantum world. In the next lecture, we will look into the mathematical framework built upon these discoveries. Thank you.